So now that we have an understanding of the macroscopic idea of what a flux integral is, now we need to get down to the microscopic level and look at the concept that we call flux density. So what is a flux density and how should we be able to compute it? Not using an integral, but using some format, some fashion of a derivative. So to get us started, there's the second activity in this section actually is just kind of a rehash of the preview activity. So rather than doing it together, we'll just sort of talk through it as a group here. I've pasted these responses into your sheets. So in the activity, what we're asked to do is consider 3 more vector fields and make predictions about whether, and if so, where are these vector fields either growing or shrinking area. Right? In other words, where will fluxes through a closed surface generally be positive if the area is growing, negative if the area is shrinking, or 0 if the area is being preserved. And so in this first vector field, zoom in on a little bit more so we can see it better. On this first vector field, it looks like everything is getting crunched. In fact, we saw this vector field as part of the preview activity. So we would conclude that this vector field is shrinking area everywhere on the xy plane. Our second vector field looks like this. We haven't seen this one yet today. But it sort of looks like that one that was circulating before, where it doesn't seem like it's either growing or shrinking area anywhere. So let's suppose that we take a little blob of ink and we place it inside of this flow right here. Let's take a look at what happens to the area of this as it flows along. Well, it's getting scrunched in one direction, but it's getting stretched in the other direction, right? It's kind of, if we go back to the beginning and slow it down a little bit, stop it right there. See how it's kind of getting stretched in the northwest to southeast direction, and it's getting squished a little bit in the northeast southwest direction. This vector field, if we test our prediction about where area is growing and where the area is shrinking, this is the vector field xy comma 1 minus x. xy 1 minus x. Give that a plot. And then we'll use, let's use our line integrals tool once again that we used in the first preview activity for today, just to kind of study where is the area growing, where is the area shrinking. And it looks like, for example, that places down here underneath the x-axis are going to have a negative total flux, which means that the area is getting squished down here. Meanwhile, above the x-axis, it looks like the area is getting stretched out, right? That the flux is positive up here above the axis. And if I have a place that's sort of right on the x-axis, it looks like there maybe the flux is equal to 0. So the purpose of this next activity is going to be to take those macroscopic observations and take them down to the micro level. And the way that I kind of have tried to walk us through this, because this is also an original Dr. S activity for this point in the course, is by first of all taking us back to how this worked with circulation. So when we first met circulation integrals, we had the total circulation, this macroscopic idea, that was the path integral on a closed loop of f dot dr. So it was a dot product of f of r of t with the tangent vector r prime of t. But then there was a circulation density function. And it turned out that that circulation density function is something we could compute with a microscopic computation, in other words, a derivative. And it ended up being this derivative of the x derivative of the second component minus the y derivative of the first component of our vector field. That's what told us the circulation density. And so coming back to what that meant, that if I want to understand what the circulation density is, I should be looking at the ratio of the circulation divided by the area enclosed by that path, and then looking at what happens to that circulation density as the size of my path approaches 0. And in our case, it looks like it depends on where our point is. Let's pick, I don't know, a point here on the x-axis. Maybe we pick the point 1 comma 0. Try and get as close as I can. And it turns out that the circulation density at that point is equal to what looks like negative 2. Right? If I take the circulation divided by the area, it looks like that circulation density is about negative 2. So we want to do the same thing with flux that we did with circulation back then. Namely, we want to figure out what it would take to turn our attention not to the parallel component but to the perpendicular component. And one way of doing that in two-dimensional vector geometry is to turn our attention away from dot products and turn our attention to cross products. So the total circulation was measured with the dot product of F with R prime. So maybe the flux, if we're lucky, can be measured by the scalar cross product of F with the tangent direction. So that's going to be the first sort of guess that we make here. If the dot product is replaced by the scalar cross product, then the first question I have for your teams is, under what circumstances will this integral be positive? Under what circumstances will this integral be negative? Under what circumstances will it be zero? And then in part B, how does that compare with the classification of flux integrals that you wrote down a minute ago? Namely, that flux integrals are large and positive when F is perpendicular to the curve, large and negative when it's perpendicular from right to left, and zero when F is parallel. So let's get you started on just parts A and B of this, what I call activity 12.5.2.5. So far, we sort of agree that because the scalar cross product is what it is, right, that the scalar cross product of vector field with velocity vector for my parametrized curve is just going to give me the product of the magnitudes of the field and the velocity vector multiplied by the sine of the angle that the vector field makes with our velocity vector. And because the sine is going to be zero anytime the field and the curve are either parallel or anti-parallel, right, 0 or 180 degree angle, then that means that this integral is going to be 0 in that case, right, where at least on a net basis, the sine of theta of t is going to be either parallel or anti-parallel. It's going to be positive when there is more of this curve along which f and r of t make an angle between 0 and 180 than not. And it's going to be negative if there is more places along this curve where the vector field makes an angle between 180 and 360 with my curve than not. So here's an example where I might ask, what is the angle between my vector field and my normal direction? Do we think that this angle should be greater than 180 or less than 180 in the particular way that's being drawn here? What would we like for this one to be? At this particular point, do we think that the flux is positive or the flux is negative at this particular point?
The flux is negative?
So talk me through that. So we're running along this curve in this direction.
Right.
And so the positive flux direction is from my left to my right. So that's why I've drawn the normal vector in this direction. And so if my vector field is flowing this way, maybe I'll put some more vector field arrows in here just for fun. We don't know what else is happening with this vector field, but let's suppose that it's doing something like that. Who knows? So we think that this flux should be a negative direction. And if the flux is negative, then what should the sine of the angle be? The sine of the angle would have to be negative. So what is the angle? What do we know about the angle? I think the angle would have to be bigger than 180, right? It'd have to be between 180 and 360. So it might be the case that what we need to do is we need to measure theta sort of counterclockwise from my normal vector. That if I measure theta in a counterclockwise orientation from my normal vector, then I'll get it right, because having a vector field, so let's suppose we have a different vector field that maybe points this way, right? Maybe this is G, different vector field, that this would have a positive flux direction, because now this angle would be between 0 and 180. Hold on. Am I happy with this? I'm not sure I'm happy with this description yet. Yeah, I don't think I'm quite getting this right. So it's really the angle in between the vector field and the velocity vector that we're interested in this activity, right? Because that's the scalar cross product that we're taking, right? The vector field scalar cross product with the velocity vector, r prime of t. And so if the angle that my vector field makes measured counterclockwise from my velocity vector, so when I do that measurement, this is the angle that I get, right? Except that now that angle is not greater than 180 degrees, is it? So somehow it's this angle that we should have been measuring. So it's measured counterclockwise from the vector field, maybe is a better way to say it. So is theta measured counterclockwise from f to the tangent vector r prime of t. If that's the convention with which we measure this angle, then having this angle be greater than 180 degrees would mean that that my vector field is flowing from right to left as we go across this curve. Because an angle of less than 180 degrees from the vector field to my tangent vector, let's suppose, I don't know, if this were my vector field, call it G, then here, if I measure counterclockwise from the vector field to tangent vector, I'm going to get a positive sign because this is going to be less than 180 degrees. Right. So this is how this idea is reifying the left to right versus right to left orientation of a flux integral. And so I think that we can sort of bypass part B because we just had this conversation. That this integral of the scalar cross product appears to line up with our intuition about what flux integrals meant. That if our vector field is either parallel or anti-parallel to the curve, then this scalar cross product is going to be 0. And so this integral is going to end up being 0 on a net basis. Whereas if it's more often the case that the scalar cross product is positive, that's because the angle between the vector field and the velocity vector is less than 180 degrees, which means that more of my vector field is crossing the curve from my left to my right as I go across the parametrized curve in the direction that it's been parameterized. And then conversely, if the angle is between 180 and 360, which means that my vector field is flowing from right to left across the curve. Okay, so examining this relationship between circulation on a macroscopic basis and circulation density on a microscopic basis, we're going to be able to get to a similarly microscopic measurement of flux density. That's going to be our next step.